Hello, welcome to our tutorial. I'm Marc Delcroix from Entity.
And I am Kateřina Žmolíková from Brno University of Technology.
So we will like to start the tutorial maybe now. So can you start the presentation? Okay. I hope you can see the slides. Welcome to the tutorial on neural target speech extraction. And first of all, I want to mention that the slides are available on this webpage, and there is also important information related to the tutorial on this webpage. So please, if you can have a look at this webpage. And if you don't remember it, we put the link below each slide. It's a bit small, but I hope you can check it. Yeah, I will skip this because you know us already. We just introduced ourselves. And we would like first to acknowledge our co-authors and colleagues, especially the members of BUT Speech Fit Group and Entity colleagues. So first, I would like to present the table of contents of this tutorial. So I will first introduce the topic, and then Katka will present audio clue-based approaches. Then we will have a short break, and she will then introduce multi-channel-based approach. I will speak about visual and multimodal-based approaches, and then we will have a discussion on other tasks than target speech extraction, which is target speaker VAD and target speaker ASR. And finally, we will conclude, and we hope to have some time for discussion and QA. So during the presentation, we would be happy if you could give a short question at the end of each part. And you can do that also during the presentation through the chat. And then we can hopefully go smoothly through the whole tutorial, and then we can have a discussion and longer question at the end of the presentation. Here in the material, you have a list of acronyms that are used during the tutorial. Okay, and now I would like to start by the introduction. In this introduction, first, I will present briefly the cocktail party and how it is related to the problem of target speech extraction. Then I will provide some notations that are used during the tutorial. And after, we'll see the relation between target speech extraction and other speech enhancement tasks. And finally, I will provide briefly an overview of datasets, toolkits, and evaluation metrics that may be helpful for doing research in this topic. So let's start with explanation of the problem. So you can see here a picture of several people speaking, having a discussion, and maybe there is television on the background. And we human in such a situation, we can focus on the voice of a target speaker, even if the people's voice are overlapping and there are several people speaking at the same time. And we can do that because of we have the selective hearing ability that enable us to focus our attention intentionally on specific sound signals. And we do that using several clues, such as locational clues. Using both our ears, we are able to decide which sounds, which direction we want to pay attention to. We also use speaker voice characteristics, so we can focus the voice on a desired speaker. And also visual clues may be also important, or even the content of the conversation. So thanks to that, we can follow a conversation in a cocktail party, or even pick up our name when it's said far away in a cocktail party, for example, even if it's very challenging acoustic conditions. So target speech extraction aims at realizing computational selective hearing, which means that we have, as seen in the figure here, we have a mixture of several speakers and maybe noise. And we want to extract speech of a target speaker in a mixture. And to do that, we inform the system about which is the target speaker using target speaker clues. So the system will input the mixture and output the speech of the target speaker only. There are various clues that can be used. For example, audio clues, that would be, for example, a pre-recorded enrollment of the target speaker voice. Locational clues, that may be the direction from where the target speaker is speaking. Or video, which may be a video recording of the target speaker speaking in the mixture. And we will present approaches using these clues in this tutorial. So you can think that it's possible to realize this using classical approaches. And indeed, if you have a microphone array, for example, you can use a fixed beamformer to extract the signal coming from a fixed direction. So in a way, this would realize target speech extraction. However, it requires knowing the position of the target speaker, which may lack of flexibility in practice. Another approach would be to use separation. So separation would separate a mixture into all of its source signals, as seen here. However, there's a few drawbacks of separation. First, separation requires knowing or estimating the number of speakers. Second, there is a speaker output ambiguity, which means that after separation, even if we perfectly separated the signals, we don't know which output will correspond to the target speaker. So if we want to realize target speech extraction with separation, we need to combine separation with another module that will identify the target speaker among the separated source signals. And if we do that, we use a cascade connection of separation and speaker identification, which may not be optimal for the target speech extraction task. So compared to that, target speech extraction exploits the speaker clue. And by exploiting the speaker clue, we avoid the limitation of previous schemes. That is, we do not require knowing the speaker location. Although some approach may use the speaker location, it's not always needed, as we will see. There is no need to estimate the number of speakers. There is no speaker output ambiguity. We only output the target speaker speech. And also, it can be optimal. It's a single system that can be optimized for the target speech extraction task. So target speech extraction was made possible recently thanks to the progress in speech enhancement, separation, speaker identification, video processing, etc. Especially deep learning enable optimized target speech extraction systems. And although there are some other ways, as we just discussed, to do target speech extraction, here we focus in this tutorial on deep learning-based approaches. And I want to mention that in 2017, we showed that using audio clues, it was possible to realize a target speech extraction. And in 2018, people showed that it was possible to use video clues to realize target speech extraction. So you can see it's quite a fairly recent field of research, I would say. And since then, there is rapid progress following the development of neural speech enhancement, separation, speaker identifications. And also there is extension to new tasks, for example, ASR, diarization, etc. So before jumping into the topic, I will like to show you one demo that will show you what can be realized with audio clue-based target speech extraction. And we present here a demo of a speaker beam method. So you can also watch this video on YouTube if for some reason it does not show very well during this presentation. So in this video, first we record the voice of the target speaker. We first record 1 or 2 sentences containing only the target speaker's voice. We then use this recording to obtain the characteristics of his voice. Then we have 2 demos. First, we have a demo of one male speaker and a female speaker, and we want to extract the voice of the target speaker. Speaker beam uses the voice characteristics of the target speaker to extract his voice, even if it is mixed with the voice of other people. Speaker beam uses the voice characteristics of the target speaker to extract his voice, even if it is mixed with the voice of other people. And the second demo is 2 male speakers with music in the background. Speaker beam focuses on the voice of the target speaker. Even if there is music playing in the background, or if someone jumps in the conversation like this, you can keep listening to the voice of the target speaker without being disturbed. Speaker beam focuses on the voice of the target speaker. Even if there is music playing in the background, or if someone jumps in the conversation like this, you can keep listening to the voice of the target speaker without being disturbed. So I hope you could perceive that it's possible to do target speech extraction, and here we informed the system only with the audio enrollment. Oh, okay. So now I would like to speak about what kind of application can be done when we, if you have a target speech extraction technology. First, of course, there is many applications for speech enhancement. So we could think that target speech extraction would be beneficial for hearing aids, hearables, for voice recorder, teleconference, where by registering the voice of the speaker we are interested in, we would emphasize this speaker's voice and maybe neglect the voice of the interference or the noise. The other type of application is for smartphone or smart speakers. And again, if we record the voice of the, for example, the owner of the device, the people of interest, then the device will respond only to the command spoken by that speaker, for example. And finally, at the end of the presentation, we will see that the IDs can also be applied for meeting ASR, where we want to record, to transcribe the speech of all the participants in a mixture. And this can be helpful to have the speaker clues to achieve that. Okay, so I briefly introduced the problem of target speech extraction. Now I would like to introduce the notations that we will use in the tutorial. And again, I take again this picture of several people speaking, and I want to emphasize what is a speech mixture. So typically, we use a distant microphone, as shown in the picture here, to record the voice of the target speaker. But the microphone signal will also include reverberation, background noise, and interfering speakers. So to really extract the target speaker voice, we would need to remove all of these interference here. But in this presentation, in this tutorial, we neglect the contribution of reverberation. Actually, some of the method can deal with reverberation, but we don't target the reverberation explicitly. So we will neglect it. So as we just mentioned here, the observed signal will consist of a mixture of target speaker in the middle here, interference speakers, and background noise. And this will be recorded by, in general, a microphone array, where M is the index of the microphone. Actually, in many cases, we will use a single channel, a single microphone, and then we will omit the microphone index M. So the speech mixture Y, or YM here, will be a sum of the speech from the target speaker, where the index S represents the target speaker, and all of the interference speaker speech. Here there is only one, but it can be more. And also the background noise. So here would be non-speech background noise. We also represent a vector Y, so boldface Y will be a vector that contains the whole signal, where T is the duration of the input mixture. Many of the approach we introduce will work in the STFT domain. So we will apply STFT to the microphone signal. And here we will represent the STFT coefficient with capitals. So capital Y will be the STFT of the mixture, etc. And again, we can represent the whole signal in the STFT domain or the spectrogram as a capital Y, which is now a matrix, F times N. Okay, so for target speech extraction, again, the goal is to, given the mixture, to extract the target speech. So the output will be an estimate of the target speech, x hat s. And to guide the system, we will inform it with audio clues or video clues, for example. And we call here C, CA, and CV the audio and video clues. From these clues, we can extract embedding, speaker embedding vectors, and these embeddings will represent the target speaker characteristics. For example, in case of audio, this vector may represent the voice characteristics. For example, is it a female voice or male voice or more detailed characteristics? This kind of information may be included in the speaker embedding. For video, this embedding will represent, for example, the position of the mouth of the target speaker speaking in the mixture. Okay, so now introduce the notation here. Now I would like to briefly emphasize the relation between target speech extraction and other speech enhancement tasks. And in particular, we will discuss briefly noise reduction and speech separation that are very relevant topics, related topics. And here we focus on neural-based approach, and in this introduction on single channel, single microphone approaches. So noise reduction, there has been a lot of work on noise reduction. And here, again, noise means non-speech noise. So typically, in the case of the noise reduction problem, or it will be a mixture consisting of a target speech and some background noise. And the aim of denoising or noise reduction is to get the target speech as clean as possible. And I will present here briefly neural network-based enhancement that use a mask to perform the denoising. So here, one way to perform noise reduction using a neural network is to compute a time frequency mask, M here. And this mask, which is represented here, is indicates where speech is dominant over noise. So M will take a 1 if speech is dominant over noise and a 0 otherwise. So if we apply this mask on the observed microphone signal, noisy speech, we can enhance the signal, reduce the noise, and enhance the signal. So this is the principle of noise denoising with a neural network, mask-based approach. And to train this kind of neural network, we typically need to have some loss function that can be, for example, the MSE, which computes the distance between the clean speech and the estimated speech x hat. And actually, the neural network can learn pretty well to distinguish speech from noise because both signals, the speech and the noise, have very different spectral characteristics. So if we feed the system, we train the system with a sufficient example of noisy speech, it can learn to capture and discriminate the two and output only the clean speech signal. The other problem is speech separation. So unlike noise reduction here, the mixture will consist of several people's speech. So here, 2 speakers. And the goal of the speech separation will be to separate this mixture into all of its sources. Again, there's lots of work on speech separation, but here I will just briefly introduce the neural network-based approach that are based on permutation invariant training. And this approach also estimate a mask, and the reasoning why we can use a mask to do speech separation, I will explain it here very briefly. It's just because of the speech sparseness property of speech signals. So as seen in this spectrogram here, this spectrogram here shows a mixture of 2 speakers. But if we look at the spectrogram of each of the speakers in red and blue, we can see that speech signals are sparse, meaning that they rarely overlap each other. So because of this sparseness property, it is possible to extract a speaker from a mixture by using a time frequency mask, which indicates when the speaker is dominant over the other. And by applying this mask on the mixture, we can extract the source. So, so this is the idea of a neural network-based approach to do separation, is to use a neural network, a separation neural network that will predict two masks, one for each of the speaker. And by applying this mask on the mixture, we can recover each of the sources. And to train this, we require to have a mixture and the source signals. And we could think that we could train it using a generalization of the loss I've just introduced for noise reduction, where we have the MSE for the first source and for the second source. But here, this assumes that the first output corresponds to the first source and the second output to the second source, which may not be the case. Actually, there is a source ambiguity, meaning that we cannot know which speaker will be at which output, and that may change depending on the mixture. So by using simply this kind of loss, it's not possible to train the separation network in general. And to solve this problem, the permutation invariant training was introduced, which is a simple approach that proposed to use the minimum of the losses computed over all source permutations. So here you can see the first term in this loss here is the loss I introduced here. So it assumes that the first source corresponds to the first output and the second source to the second output. And the other term here is just the opposite. So the first source corresponds to the second output and the second source to the first output. So we can compute the loss for both of these terms, and we take actually the minimum and just backpropagate using the minimum of these two. And by doing this simple modification of the training objective, we can actually train a separation network. And this can lead to quite a good separation performance. Here, I will show you one example of a speed-based separation using a relatively like kind of a first kind of model generation of model. So it's not the best type of separation model we can use now, but it already gives you an example of how separation can work. So first, I will play the mixture.
Monday's crash is likely to affect at least one other piece of pending legislation.
And then the first speaker.
In recent years, she had primarily appeared in television films, such as Little Gloria.
Monday's crash is likely to affect at least one other piece of pending legislation.
So I think you can perceive that the separation works quite well. But again, this is definitely not the best you can do. There are actually a lot of work that improved over what I've just showed you. And one example of this is a method that works in the time domain. So time domain separation, such as TASNet or conv-TASNet. And the idea of conv-TASNet is to replace the STFT and inverse STFT by learnable encoder and decoder that are actually 1D convolution layers, and to directly accept the time domain mixture and output the time domain sources. And by doing that, we can estimate also the phase of the signals. And this is actually a very powerful approach that leads to very good separation performance. And on top of that, the training is also using permutation invariant training or PIT loss, but it is done in the time domain. And to compute the difference between the source and the prediction, it used the SDR or signal to distortion ratio that measure here the ratio between the source X and the distortion or error, which is, the error which is, okay, this error here is the difference between the source and the estimated. So directly estimating this SDR in the training. So I briefly introduce you some separation approaches, and we saw that there are many different ways to implement it. So we showed 2 approaches, but there are actually many different architectures and also different losses and configurations. And here it is important to know that the problem of target speech extraction can borrow the architecture and loss developed for separation. So it's good to follow the work done in separation, and then you can get the best architecture and try to apply it for the target speech extraction. So now, as I briefly mentioned at the beginning of the introduction, it's possible to do target speech extraction by combining separation and identification. As I mentioned, separation itself cannot, at the output of the separation, we don't know which output corresponds to the target speaker. Even if you use the permutation invariant training, we don't know which output is the target. So it requires to have a speaker identification as post-processing. And this post-processing here will use the target speaker clue to say which of the output corresponds to the target speaker, for example. But there are some drawbacks with this scheme. First, you can see that the target speaker clue is used only in the speaker identification part. Although this speaker clue can provide quite important information that could help the separation, it is not used in the separation. Also, this is a cascade connection of 2 modules that is not jointly optimized. An error performed in the separation will accumulate and would degrade the performance of speaker identification. So this is not an optimal scheme. Also, the separation, as I mentioned before, it requires knowing or estimating the number of speakers, which may be a very practical issue. So if compared to separation, target speech extraction exploits the speaker clues, but it realizes the separation and identification at once. So this is potentially a more challenging problem because, of course, we combine both problems. So we need to not only separate well, but we also need to identify well. But because it uses the separation clues in the module, integrated modules, it can exploit the clue also to perform better extraction. And also the whole system can be optimized for the target speech extraction. And if we compare separation with Oracle target speaker identification, so this would be the upper bound performance of a method that combines separation and identification, and we compare it with a comparable system using target speech extraction. So here we have 2 examples of this system, one in the frequency domain and one with ContastNet in time domain. We see that using the target speech extraction usually gets a better performance than using the separation plus Oracle identifications, which really show that using this jointly optimized and single system can be very beneficial. We can also compare target speech extraction to noise reduction. And here, similar to noise reduction, there is only one output, which means that there is no speaker ambiguity. And also, we do not need to estimate the number of speakers in the mixture. So here we have a table that summarizes the property of the different speech enhancement tasks. And we can see the target speaker extraction target a mixture of more than one speaker with an unknown number of speakers. There is no target ambiguity at the output. And to realize that, we need to have some speaker clue. Finally, I would like to briefly introduce dataset, toolkits, and evaluation metrics. First, the dataset. I would like to say that there are actually no common dataset for target speech extraction, but we can use most datasets that are used for separation. So here, I list briefly a list of the most common datasets that are used, either as it is for separation or that are used to design data for separation. And you can actually use these kind of data set to evaluate target speech extraction, train and evaluate target speech extraction. And I want to say just a word about how we can simulate a mixture or create a simulated mixture. So first, we assume we have a data set that have several speakers and several utterance per speaker. So we'll sample one utterance of the first speaker and one utterance for the second speaker, and we can mix these by varying the gains to vary the signal to interference ratio and eventually adding noise or reverberation. And that will give us the data that is typically used to train or evaluate speech separation. And to do target speech extraction, on top of that, what we need to do is to get a target speaker clue. And for example, for audio-based approach, it can be done by randomly selected another utterance of the speaker 1 and another utterance of speaker 2, and then we can do target speech extraction for the first speaker or for the second speaker. As for the toolkits, here I list a few of the toolkits that are widely used for speech enhancement and ASR. And again, here there is no official recipe for target speech extraction or target speaker ASR in these toolkits, but it's quite easy to modify an existing recipe for separation to make it work for extraction. And we will see at the end of part 2 one example of how this can be done. And we provide here an example which is based on asteroid. Finally, in terms of evaluation metrics, many of the approaches are evaluated using the signal to distortion ratio or SDR or some variant of it. But also sometimes the method may be evaluated with SPESC or for speech intelligibility with STOI. And for ASR, the word error rate is also, of course, widely used. So Katka will speak a little bit more about the SDR in her part. So this is the end of the introduction. After each section, we listed the main references. So if you can access the material, which is available on this webpage here, you can get more details by looking at the references. And if you have any questions about what I've just said now, it's a good time, and you can also pose questions in the chat. So I don't see any questions, so maybe we can continue with Katka, and if you have questions, you can still put it in the question. Oh, hello?
So we can maybe continue with the second part now.
Oh, yes.
Okay, good. So the section 2 of the tutorial will be about target speech extraction with audio clue-based approaches. First, let me just remind ourselves what the task is about. We are doing target speech extraction, so on the input we have okay, I will not use this. On the input we have a mixture of multiple speakers, and our desired output is the speech signal of the target speaker only. To determine the target speaker, we have an additional clue, which in this section will be audio clue. Audio clue means a short utterance spoken by the target speaker. We will call this utterance enrollment utterance, and in practice it can be, for example, pre-recorded by the target speaker. This section will have two main parts. In the first part, I will go over several aspects or choices that we can make in the target speech extraction models. And in the second part, I will show a few examples of existing models. There are 5 different aspects of the models that I will cover here. The first one is how to extract speaker embedding from the enrollment utterance. Then second, how to use this embedding to inform the neural network about the target speaker and so guide it to extract the signal of the target speaker. Then I will talk about the different domains in which we can represent the input and output signals, and related to that, which loss functions we can use to train the parameters of the neural network. Finally, I will show several neural network architectures that are commonly used for this task. First, let's talk about speaker embeddings. The goal here is to take the enrollment utterance and extract an embedding which encodes the information necessary to identify the target speaker in the mixture. Naturally, this information should be speaker information, so the vectors or embeddings that we use here are often inspired or taken from a speaker verification field. There will be two vectors that, or two methods that I will talk about that are inspired from speaker verification: I vectors and neural network-based embeddings such as X vectors. And the third option are embeddings which are jointly learned with the task of target speech extraction. I vectors are speaker embeddings that for a long time were considered state-of-the-art for speaker verification, and until today they are still often used for speaker adaptation in speech recognition models. The extraction of the I vectors is based on a generative model, in particular a Gaussian mixture model, GMM. The extraction then goes in two steps. In the first step, a universal background model is trained. A universal background model, or UBM, is a GMM which is trained on a large data set of many different speakers. After the UBM is trained, we can actually extract the I vector from the input utterance by fitting a GMM to the input utterance, but here the GMM is constrained by the previously trained UBM. In particular, we have the different components of the UBM can be shifted in a constrained set of directions, and how much we shift the components in these directions, these are the values of the I vector. One interesting property of the I vector is that we don't explicitly use the speaker information at any point in the training or the extraction of the I vector. So the I vector can contain also other information such as channel information. This can be often undesired, but in some use cases it can be beneficial to also have the channel information in the embedding. Eventually, the speaker verification community moved to speaker embeddings which are neural network based. Maybe the most popular neural network based speaker embedding is X vector, but in the target speech extraction field, embedding which is also often used is D vector. Both of these embeddings are based on a neural network which is trained for the task of speaker classification. After the neural network is trained, when we want to extract the embedding, we forward the sequence of features through the neural network and extract the embedding as hidden representations at one of the last layers of the network. One important component of the neural network is a pooling layer, which converts the sequence of activations into one vector representing, the entire sequence. The specifics of the model, such as the neural network architecture, the loss function, or the type of the pooling layer may differ, not only between X vectors and D vectors, but also between different variants of X vectors and variants of D vectors. But as one example, the very original model of X vectors used a convolutional architecture where the loss was categorical cross entropy, and the pooling layer simply computed mean and standard deviation over this sequence. The good thing about this type of embedding is that it is very highly speaker discriminative because it is trained for speaker discrimination, and also you can often find pre-trained available models for example, X vectors, which are trained on very large data with many speakers and many different conditions, so the vectors that you get are quite robust. One possible disadvantage is that these embedding extractors are trained for a different task, for speaker classification, while we want to use them for target speech extraction. So they might not be the very optimal representation that we can get for target speech extraction. And this is the thing that is basically addressed in the last option for the speaker embeddings, which are embeddings jointly learned with the task of target speech extraction. In this case, we are not using any external pre-trained model, but instead we use an auxiliary network which takes the enrollment utterance at its input, and it is adjoined to the main neural network which extracts the signal of the target speaker. Both of these networks are then jointly trained for the task of target speech extraction. The auxiliary neural network here should learn to extract the speaker information because that's the type of information that is needed in the main neural network to extract the speech of the target speaker. It has been actually shown in several works that the auxiliary neural network actually learns that. Here on the slide you can see a TSNE plot of the extracted speaker embeddings where the different clusters are the different speakers. The jointly learned embeddings are perhaps the most popular choice in the target speech extraction literature. One possible disadvantage is that here you need to train the embedding extraction on the same data on which you train the target speech extraction task. And very often these data sets do not have so many speakers or so many variability in the conditions. So using the pre-trained embeddings such as X vectors may be sometimes more robust. So this first part was about how to get the speaker embedding from the enrollment utterance, and now we will look at how to use this embedding in the main neural network. The goal here is basically to modify the forward pass through the neural network in such a way so that it extracts the signal of the target speaker. There are different ways to do this, and I will cover 4 different methods: concatenation, factorized layer, multiplication, and attention-based. First, let's still look in a bit more detail on the neural network. So on the input, we have the mixture of multiple speakers and the speaker embedding. And eventually, inside the neural network, we want to modify one layer using the speaker embedding. We will call this layer adaptation layer or fusion layer. The term fusion layer is mainly used in audio-visual works that you will also hear about in the next part of the tutorial. The position of the adaptation layer in the network varies, but most often it would be either the very first layer of the network or one of the early layers, like in the first half of the neural network, or in some works it is simply all of the layers, so basically the entire neural network is being adapted. The first method for informing the neural network is concatenation. This is maybe the simplest of all the methods. Here we concatenate the embedding on the input of the adaptation layer. This can be also seen as a modification of the bias of the layer because the embedding times the weight matrix or the part of the weight matrix associated with the embedding is added to the normal output of the layer. So this basically just adds a bias to the layer. This can be seen as a disadvantage because we are only adapting a very small fraction of the parameters of the neural network. What we want to do is to completely switch the output of the neural network by just changing a bias of one of the layers. Nevertheless, the concatenation is still successfully used in many different methods. So whether this method is strong enough to actually change the output of the network may also depend on particular architecture, particular data that we have. The next method, factorized layer, in some sense goes to the very other extreme. In a factorized layer, we are actually modifying all of the parameters of the layer. In a factorized layer, what we do is that the adaptation layer is replaced with several sublayers, and the final output of the layer can be obtained as a weighted combination of the outputs of the sublayers. The weights of the combination are determined by the speaker embedding. The parameters of the sublayers here can be also seen as some basis of a subspace of the parameters of the neural network, and the speaker embedding then determines where in this subspace we take the parameters. In this method, the speaker embedding has really a very strong influence on the parameters. It basically completely changes the parameters of the layer, but the disadvantage of this method is that it is very memory expensive because we need to store the parameters of all of the sublayers. The next method, multiplication, is in some sense a compromise between the previous two. In multiplication, we multiply activations in one of the layers of the neural network with a speaker embedding. This can be also seen as modifying the weight matrix which is in the neural network before the multiplication. Here again, the speaker embedding has quite a strong influence on the processing of the neural network, but at the same time it is still quite simple. The multiplication is just a simple operation and we do not have any additional parameters here. There is one more variant of this called film, feature-wise linear modulation, where also after the multiplication there is addition. The film method is very commonly used in other areas such as voice conversion or image processing, and it is essentially very similar to the simple multiplication. One drawback, and now not only of the multiplication-based method, but actually of all the methods that I presented until now, is that the same modification is applied to all time frames. And this is something that is addressed in the attention methods, and I will now try to describe it a bit more in detail. So on the input of the neural network, we have a mixture, which is a sequence of features. So at each layer of the neural network, we get a sequence of representations. And in all of the methods that I presented until now, we have also enrollment utterance, which is also some sequence, and we use a pooling layer or some kind of pooling on the enrollment utterance to get one embedding. Then we apply this embedding in the same way to all of the elements of the mixture sequence, to all of the time frames. This may not be the best thing to do because we are basically here completely disregarding the dynamic information which is in the enrollment utterance. If you imagine, for example, that in the current mixture frame, both of the speakers are pronouncing a vowel, then maybe we want to look into the enrollment utterance to the parts where the target speaker is pronouncing a vowel, because that's a useful information to differentiate between the speakers in the current frame. And this is something that the attention-based schemes are trying to do. In the attention-based schemes, we disregard the pooling layer, and instead we apply attention over the enrollment utterance, which is queried by the current mixture frame. As a result, we get a specialized speaker embedding for each time frame of the mixture. And each of these embeddings is obtained by looking at the different parts of the enrollment utterance using the attention. Then, if we have special speaker embedding for each time frame of the mixture, we can apply this different embedding to each time frame of the mixture. And here I have as example on the picture multiplication, but the same thing then could be done also by concatenation or the factorized layer. Here just note that the attention-based method is not directly applicable when we use I vectors or X vectors as the speaker embeddings, because these already inherently have the pooling in them. They are already only one vector. So when we want to use the attention-based method, we learn the speaker representations jointly with the full model. So this finishes the part about informing of the neural network, and I will now shortly talk about the domains in which we can represent the signals. There are two main domains that are being used, frequency domain and time domain. Frequency domain means usually magnitude of short time Fourier transform of the signal or log magnitude of STFT. This has been used a lot in the past, but in recent years, more and more work started to use time domain models. In the time domain models, the input of the neural network is directly the raw signal. The first layer of the network is then a convolutional layer, which is usually called encoder. This layer can theoretically even learn the same transformation as the short time Fourier transform, but since it is learned, it has more freedom, so it can also learn something that is closer to optimal for our task. One difference that can be also very often seen in the literature is that the time domain models usually use much smaller windows in the encoder. Here the windows are usually in order of milliseconds, sometimes even only a few samples of the signal. While in the frequency domain approaches, the short time Fourier transform would usually act on much larger windows than that. Other aspect, which is also a bit related to the domain, is a loss function that we use to train the parameters of the network. The loss function should basically measure the discrepancy between the estimated signal and the reference signal. There are different loss functions that are used when we use frequency domain approaches and time domain approaches. In both of these cases, the loss functions are similar or basically the same as the loss functions used for speech separation. Just in this case, we do not need to use permutation invariant versions of the loss functions as in speech separation, because on our output we have only one signal of the target speaker. In addition, for this task, one additional loss that we can use is speaker ID loss, which is applied on the speaker embeddings and deals with the speaker information in the speaker embeddings. But first, I will still talk about the loss functions that measure the discrepancy or the quality of the output signal. And first, I will start with the frequency domain approaches. When the neural network acts on frequency domain, there are basically two possibilities of what can be on the output of the neural network. Either the neural network directly estimates the enhanced magnitude STFT of the signal, or the neural network outputs a time frequency mask. If it directly estimates the magnitude of the signal, then the most commonly used loss function is mean square error between the enhanced magnitude and the magnitude of the reference signal. When the neural network estimates time frequency mask, which is maybe even a more common option, then we can also compute the loss function directly on the masks. For example, by using binary cross entropy between the estimated mask and ideal binary mask. Or we can apply the mask on the mixture magnitude by multiplying it with the mixture magnitude, and then again compute mean square error between this enhanced magnitude, the result of application of the mask, and the magnitude of the reference signal. In time domain, the most commonly used loss function is scale invariant signal to noise ratio, or SI-SNR. This loss function measures the ratio between the energy of the reference signal and energy of error, where the error is simply a difference between the estimated signal and the reference signal. Here, all these signals are in time domain. There is one more thing about this loss function. The reference signal is not taken just as is. This X is the original reference signal, but we multiply it with a coefficient which maximizes the SNR. You can see it on the picture on the right. In the picture, the light blue arrow is the estimated signal, the dark green arrow X is the original reference signal, and the light green arrow is the reference signal after the scaling. And you can see that we scale it in such a way so that we minimize the error between the estimated and the reference signal. This is done because usually we don't care so much about the exact scale of the signal, so we allow the loss function to correct for this scale factor. In addition, in the target speech extraction method, we can also use loss function that encourage the speaker information in the speaker embeddings. This can be used in the methods where the speaker embeddings are jointly learned with the task. So when we have the auxiliary network that learns to extract the speaker embeddings. When we want to apply the additional speaker ID loss, we add a layer or few layers after the speaker embeddings, and we use additional loss which measures quality of speaker classification. In the literature, there have been different loss functions for this explored, such as categorical cross-entropy, large margin cosine loss, or triplet loss. All of these losses are inspired from speaker verification literature. Finally, I will describe several neural network architectures that are commonly used for this task, namely BLSTM, ConfTasNet, and Dualpath RNN. Here, these architectures are basically the same architectures that can be used for speech separation, so I will not go into many details about the architectures. BLSTM is a recurrent architecture. It has been used a lot in early works that worked on frequency domain. Basically, the neural network here consists of a stack of several BLSTM layers. When we also use the auxiliary network, then the auxiliary network can either also incorporate the BLSTM layer, or in many works, the auxiliary network is simply, in this case, just a stack of few fully connected layers. For the time domain, the most commonly used model is ConfTasNet. ConfTasNet is a convolutional architecture, so it consists of a stack of many convolutional blocks, where all the convolutional layers have some dilation factor. The dilation factor is used so that we increase the receptive field that the neural network sees. Typically, for ConfTasNet, the receptive field would be in order of seconds. This depends a lot on a particular architecture, like how many layers we use and things like that, but usually it would be somewhere around 1 to 10 seconds. When we also use the auxiliary network in the architecture, for this model, usually as the auxiliary network, we would also use a similar stack of convolutional layers. The last architecture, which is starting to be used in recent years, is Dualpath RNN. It is a recurrent architecture, and I will not go into many details here, but basically the architecture is designed in such a way so that the model can well model very long-range dependencies. Because of this, it is very useful for time domain representation, and especially it also allows us to use very small windows in the encoder, because that then leads to very long sequences, and Dualpath RNN can deal with these very long sequences. For more details, I will just refer to the original work that proposed the Dualpath RNN architecture. This concludes the first part of the section, and now I will move on to the second part, where I will show several examples of existing models for target speech extraction. We have chosen 3 of these models: Speaker Beam, Voice Filter, and Speaker Inventory. Speaker Beam is a model that has been proposed by us in 2017. In this paper, we developed the idea of using the speaker embedding to extract the speech of the target speaker. In this paper, we have compared this to some previous methods for target speech extraction that are applicable only when we have closed set of speakers, such as training a separate neural network for each target speaker. And basically, we have shown that if we use the speaker embedding in the neural network, then it allows us to extend this also to open set of speakers, so to speakers unknown in the training. Later, we extended the method. We compared it also to speech separation methods and integrated it with multi-channel processing or speech recognition. I will now classify this model into these different categories that I talked about in the presentation. Speaker Beam uses jointly learned speaker embeddings. For informing the neural network, the early version used factorized layer, and then we opted for multiplication-based informing of the neural network. There are both frequency and time domain versions of speaker beam, where the frequency domain versions use mean square error as the loss function together with BLSTM architecture, and the time domain speaker beam uses SI-SNR as the loss function together with conv.NET architecture. Here you can see an example scheme of time domain speaker beam, where also the speaker ID loss is used here. Here we have some results of time domain speaker beam, which are results on multi-channel Wall Street Journal 2mix dataset, which includes also some reverberation. And here the evaluation metric is SDR, so the higher the better. We can first look at the last column, which compares the average SDR over the set for different methods. So the very last row here is the performance of the time domain speaker beam, and we can compare this with the row 2 and 3, which show performance of a cascade of speech separation and a subsequent selection of the target speaker, where in the second row, the target speaker is selected from the outputs of speech separation in Oracle way, and in the third row it is selected by using X vectors. So here you can see that doing the target speech extraction directly has some advantage to the cascade of speech separation and selection. Also here you can compare frequency domain and time domain speaker beam. At least on this particular data set, the time domain speaker beam has quite significant advantage over the frequency domain one. What is also interesting is to look at the split of the results over different parts of the dataset, and here we split it into different types of mixtures: female-female, male-male, or female-male. And you can see that if we have a mixture of different genders where the voices of the speakers are more different from each other, then the target speech extraction works significantly better. This is something where there is still some room for improvement in discriminating better speakers that have similar voices. The next model that I will show here is voice filter that has been published in 2019. Here you can see overall scheme of the voice filter, and I will again categorize it into the different categories that I introduced in the presentation. Voice filter uses D vectors as the speaker embeddings, and it uses them in the neural network by concatenation. It works on a frequency domain, so the input is magnitude STFT of the signal, and the loss function is mean square error. The architecture used in voice filter is a combination of convolutional layers and LSTM layer, where there are 8 convolutional layers and 1 LSTM layer, and the speaker embedding is applied after all the convolutional layers before the LSTM layer. Here you can see some results of voice filter, both SDR results, which measure the quality of the extracted signal, and word error rates, which show the result of automatic speech recognition applied on the extracted signals. Here you can see that the quality of the signal after applying voice filter is significantly better than the quality of the original mixtures. And also the speech recognition results are very significantly improved after applying voice filter, from 55% word error rate to 23% word error rate. The last model that I will introduce here is speaker inventory. The speaker inventory takes slightly different approach than the other models. Up until now, I was defining the target speech extraction as extracting the signal of target speaker while having information about the target speaker. In speaker inventory, the authors assume that we have also some information about the competing speakers available. This can be useful in some use cases if you imagine, for example, a meeting where you can have some knowledge also about the other speakers that can take part of the meeting. The speaker inventory is also one of the first papers that introduced the attention mechanism to inform the neural network. In these results, you can compare the quality. These are SDR results, so again, the higher the better. And you can compare the quality of the output signal when we use only the information of the target speaker, and if we also added the information about the competing speakers. So you can see that adding the information of about the competing speaker significantly improves the performance. And the third result shows the result if we do not know who exactly is the competing speaker, but we have some inventory of possible competing speakers. In this case, the result is slightly worse, but still significantly better than not having any information about the competing speaker. This concludes this audio part. The main message should be that target speech extraction can be realized when we have audio clue about the target speaker. The models combine methods from speaker adaptation, speaker verification, and speech separation or enhancement. The current challenges still are better discrimination of similar voices or also robustness to very noisy or reverberant conditions. There is a lot of existing work, and in this presentation I didn't have time to cover all of that. For example, deep extractor network, SPX, or speaker filter, and others. But we also created a compilation of references that you can find at the link that is also available at the website of the tutorial. And you can get to this Google Sheet that also categorizes the different references into the categories that I have introduced in this presentation. With the tutorial, we are also releasing implementation of SpeakerBeam, so you can yourself play with the model. The implementation contains Timedomain SpeakerBeam model, also some alternative adaptation layers such as concatenation layer, and a recipe on a Libre2 mixed dataset, which contains also the dataset preparation for the task of target speech extraction. So also, for example, the map from the mixtures to enrollment utterances. The implementation is based on Asteroid Toolkit, which is a toolkit for speech separation that I also recommend everyone to check out. In the repository, you can also find a notebook with example inference using SpeakerBeam, and I will now also play one example that you can also find in the repository. So first, the mixture signal.
If the wine changes into vinegar, the host crumbles into corruption after they have been.
Then the enrollment utterance.
Then you can ask him questions on the catechism, Daedalus.
And the estimated signal of the target speaker.
If the wine change into vinegar, and the host crumble into corruption after they have been.
In the repo, you can also find other examples or just try out on your example. And with this, I will just conclude this section. And if you have any questions, then now we hopefully have some time to address a few questions.
Katka, there were a few questions. Can you hear me? Katka. Okay, there were a few questions in the QA, so maybe it's good to, I tried to answer it already, but maybe it's good to mention it. So I just want to read them. So Daniel mentioned as what output do you expect for the presented TAC system if you provided clues that do not correspond to the target speaker present in the mixture? And I just mentioned that this is a very good point, and that actually we just mentioned briefly this problem at the end, but we would expect to have a zero signal, but most systems do not evaluate this case, I would say. I think there is one presentation that actually deal with this in this conference. I don't know if you have other comment about this.
I think this is maybe one point that still kind of waits to be researched further, because many works do not evaluate this case, and it can be also important case to address.
Mm-hmm. So already we have a discussion, like some of the conclusion part is already covered. So the other question was, what is the minimum size in seconds of the audio or video clues? And okay, so maybe actually I just partially answered this question, and I said the duration of the enrollment depends on the studies. It can be only a few seconds, like less than 10 seconds, and some studies use even shorter or longer enrollments. So for the audio, I think that's basically.
Mm-hmm. So if you look at our SpeakerBeam journal paper, we did also some analysis of this. It's already a bit older model, but I think that from like 2 seconds, the extraction was already reasonable. And for example, deep extractor model also tested shorter adaptation utterances around less than 1 second.
Mm-hmm. And actually, I didn't answer for the video. And actually the video is the video of the people speaking in the mixture. So the duration of the video is the duration of the mixture. I will explain that afterwards. I hope it's become even clearer. And then there are two questions about the mask loss. So from your experience, are the mask cross entropy loss function and the masked mean square error equivalent? How to choose which one to prefer via validation? And another question, another kind of related question is, for the frequency domain losses shown, the magnitude mask is used. From your experience, do you see benefits of estimating complex masks rather than magnitude masks? And at least I answered that, and you can correct me, the mask cross entropy loss and the masked mean square error are not equivalent. I don't remember, and then I don't remember if we compared magnitude and complex masks in our studies, but other reported that complex masks worked a little bit better, I think. But we can discuss more now.
So one thing that is very popular not only in the mask-based losses but also in the magnitude losses is to somehow also include the phase information. These are called phase-sensitive mask or phase-sensitive mean square error loss functions, and I would say that these are actually very often used and shown to be slightly better than just using the masks that do not incorporate the phase information. Then I think I wanted to say something between the mask cross entropy and the mask mean square error. So as Marc said, these two are not equivalent, and in most of the literature that I have seen, I think that what worked better is to use the masked mean square error. So maybe rather in the earlier works the mask cross entropy was used, and in the later works rather the masked mean square error.
And I would like also to maybe say that you can actually use, for example, SDR or SISNR to optimize the network, even if you do it mask prediction, and even if the extraction is done in the frequency domain, you can do the inverse STFT and backpropagate through the inverse STFT, because current toolkits are very flexible. So even if you want to estimate the mask, you can still use time domain loss. Then maybe the last question is, how well does TSC perform on very short speech? Example, speaking just one word in a noisy environment.
So we already talked about the duration of the enrollment utterance now in the questions. For the duration of the mixture, I don't think that this really matters so much, because, for example, the conf_tasnet, which is very often used, very often an architecture would be used that has a receptive field around 1 second. So actually, if you use longer utterance, you don't have so much advantage, because the neural network anyway sees only 1 second at a time. So I don't think that these short mixtures should be much of a problem.
And then we got, we got another question just in, and this is, did you apply any of the time domain method on narrowband data? Example, data went through GSM A-low or U-low codecs, and at least I think we have not. I mean, I'm sure we have not, but I'm not sure if other people have done it. And yeah, I don't know if Katka have seen any work that did that.
I don't really have much insight about this. I haven't seen works that would address this problem.
So I'm not very I'm not used to work with codec so much. I would say that probably if you train the system with the appropriate codec or with multi-condition data so that it sees this kind of codec, I would expect the method to work well. But maybe if you didn't provide any of this data during training, then probably it will be an issue. Yeah. Is it? And then one more question is it possible to allow some noise with Tasnet? I think here, do you mean that the mixture would include not only an interference speaker, but also include noise? and I think it is possible.
Yes, that is possible, even in the example that, like in the recipe that we are now providing with SpeakerBeam, this is trained on noisy data. But I am not 100% sure if the question meant that or meant to allow some noise on the output of the neural network.
Oh, yes, that's a good point.
Maybe if it was about the output, you can still write to the chat and we can address also that case.
Yeah, I think we should also be able to accept audio questions. I mean, I think if people turn on their microphone somehow, I'm not sure. But anyway, I want to mention that actually now is kind of, we can have actually 5 to 10 minutes QA or break times. So if you have more questions, it's actually a good timing. And then probably from in 10 minutes or maybe a bit earlier, we will start again with the next part, I would say. So, and then the question is, if we want to allow some music on the output. So do you mean like outputting speech and music?
Yes, I think that's the question. So for music, so we definitely didn't explore that, and I'm not sure if any work did, but I wouldn't think that it would be such a problem to also include music at the output if we have training data which are constructed in that way. I think if it was not music but some noise, it could be a bigger problem, and some works more in the separation area showed that having noisy references can be a problem and can degrade the performance of the separation. But I think that music is like enough structured signal so that the neural network should be able to learn to also output that. But that's just like I do not really have any experience. That's just my opinion.
Yeah, I think this kind of situation, you need to deal with the kind of training data you provide to the system. Oh, sorry, that was from me. So by carefully designing the data, and maybe need to change a little bit the output, so have an auxiliary output at the system for the music part or something. Maybe it is possible to address this kind of issue. But again, we haven't really dealt with that really. And then on the output, I assume you mix the resulting audio. I'm not completely sure what it's meant by that. You mix the resulting audio. Do you have an idea of what that could mean, Katka?
Not really. So
is it something like adding the mixture and the enhanced speech or something?
It was some additional comment to the other question, so hopefully we have already answered. I think it was just a specification of the question of the allowing of the noise.
Okay.
So I think these are all the questions so far. So maybe now we can allow a 5-minute break.
Yes, we can allow 5-minute breaks, and if you have questions, you can still post it in the chat. I don't know if it's possible to have actually comments or like question live, but yes. Okay, can you please tell shortly about dataset used to evaluate research work on NTS? So I think one of the very widely used data sets, NTS, maybe I'm a bit out. I'm not completely sure what you mean by NTS. But for target speech extraction dataset, one of the widely used one is actually the Wall Street 02 mixed that was created by Merle. And then, yes. But people also get their own dataset, so there is actually not really an official dataset. So the Wall Street Journal 2 mixed is actually created for separation. So there is no official list of the enrollment that should be used for evaluating the target speech extraction. But people usually simply randomly select one utterance for the target speaker from the speaker in the mixture.
Yeah. So also, if you check the Google sheet that we published and that we have a link to on the tutorial website, with the references, there is also one column specifying on which data set they tested. So you can just check there which are the most common data sets, but it would be usually either the Wall Street Journal or just some custom data set. And maybe recently also the Library 2 mix.
So we have a list in the material on slide 46 about the list of the data sets. So maybe that can be a hint. Okay, good.
Then you can ask him the question.
Okay, we can continue. Sorry for the rather short break, but we have a lot of content to cover, so we should continue. The section 3 of the tutorial will be about target speech extraction with multi-channel approaches. In multi-channel approaches, we assume that we have a mixture recording which was recorded with multiple microphones. Having this multi-channel recording allows us to also use spatial position of the sources to better extract the target speaker and to better remove the other sources. There are different ways to use the spatial information, and I will talk about 4 different approaches: mask-based beamforming, spatial features, fixed beamforming with stream selection, and location-guided methods. In these 4 methods, the first 3 assume having the multi-channel recording, but they do not assume having any information about the position of the target speaker. In contrast, the 4th class of approaches, location-guided methods, these also assume that we have some spatial information about the target speaker as part of our enrollment. But first, I will go over the first 3 approaches, and I will start with mask-based beamforming. Because this tutorial is mainly focused on neural methods, I will also talk about neural mask-based beamforming. This method was proposed by Jan Heyman and Hakan Erdogan, and in this method, the neural network processes multi-channel signal, but it processes it by each channel independently. So on the input of the neural network, we have only a single channel. The neural network then estimates time frequency masks, 1 for each channel, and these masks that can be aggregated using, for example, median operation over the channels. This aggregated time frequency mask is then used to compute weights of beamforming filters, and finally these beamforming filters can be applied on the multi-channel signal to get the final enhanced signal. I will describe this a bit more in detail, and I will start from the back, from the beamforming. There are many possible beamformers that can be used. Here, as an example, I have MVDR beamformer, and this formula shows one possible formulation of the MVDR beamformer that has been published by Mehrez Sudan. Here, I will not go into very details about how this formula is derived, but what I would like to mainly emphasize are the quantities that we need to compute the beamforming filters. In this formula, the vector I is a one-hot vector that denotes a reference channel. The reference channel would be usually selected to be the microphone with the best quality of the signal. The other 2 quantities that we need here are RVF and RSF, which are the cross-power spectral density of interference and cross-power spectral density of the target speech for frequency bin F. These cross-power spectral densities are square matrices of the dimension of the number of channels. They can be estimated with these 2 formulas that you see here from the observed signal, where the different time frequency points of the signal are weighted with a time frequency mask. Here, this MTF should be the probability that the target speaker is dominant in this time frequency point. And this time frequency mask, MTF, is what is estimated by the neural network, and it is where the neural network output enters the computation of the beamforming filters. The neural network itself, as I already mentioned, on the input has a signal channel only, so it processes each channel independently. And as a target for training this neural network, we can use, for example, ideal binary masks, where ideal binary masks simply in each time frequency point have either 1 when the target speaker is dominant in that time frequency point, or 0 in other cases when the target speaker is not dominant. For the loss function, we can use binary cross entropy between the estimated mask and the ideal binary mask. There are also some alternatives to this approach. For example, there are also time domain versions where a time domain neural network, output of time domain neural network can be used to estimate the beamforming filters. Or there are also some approaches that do not compute the loss function directly on the masks, but rather than that, they compute the loss function on top of the enhanced signal after the beamforming. To do that, what you need is to be able to differentiate through the estimation of the beamforming filters and the beamforming operations, but in some works this has been explored and shown to be possible. Here you can see just an example of some results obtained using mask-based beamforming. This is on the multi-channel Wars regional 2 mix, and these results are word error rates of automatic speech recognition system ran on the signals. So you can see that on the original mixtures, the word error rate is very, very high, 85%, because here the speech recognition system basically doesn't have a way to differentiate between the target speaker and the interference. Kind of an upper bound of the performance is the performance on single speaker clean signals, which here is 16% word error rate. And if we apply the mask-based beamforming together with speaker beam, you can see that we can get quite close to this 16% to 22% word error rate. Another possible approach is to use spatial features. In the mask-based beamforming, I mentioned that the neural network processes each channel independently. This is by design, and it has some advantage, in particular that the neural network is in no way dependent on the configuration of the microphone array, like the position of the microphones, and it cannot really overfit to a particular microphone array, so we can also apply it to different microphone arrays. On the other hand, the neural network doesn't use in any way the spatial information that is used only in the beamforming. And the neural network could also benefit from using the spatial information, and it could do better estimation by using the spatial information. So a way to do this is to extract some kind of spatial features from the multi-channel signal and to use them on the input of the neural network. This kind of approach has also some, I would say, danger. When we do that, the neural network may learn to over-rely on the spatial features. It has been shown on some works that if we use the spatial features, then actually if we apply the neural network to mixtures where the speakers are not very well spatially separated, they are speaking from the same direction, then the performance can deteriorate a lot and be even like significantly worse than a neural network which doesn't use the spatial features at all. This can be overcome, for example, by more careful design of the training data, but it is something to be aware of and to be careful about. For the spatial features itself, we can either use fixed spatial features or learned spatial features. For the fixed spatial features, the feature that would be most commonly, almost in all target speech extraction works used, is interaural phase difference, that for each time frequency point measures the difference of the phases at two microphones, microphone 1 and microphone 2. If we have more than two microphones, we can just select several pairs of the microphones, extract the IPDs from these pairs, and then concatenate the IPDs from different pairs. There are other options like interaural level difference or generalized cross correlation, but these are quite rarely used. To see that the IPD actually encodes some useful information for the extraction, we can look at this image here, which shows for each frequency bin a histogram of the IPDs of all the time frames. The different points here are colored by the speaker, which is dominant in the time frequency bin. So here you can see, in this example, the speakers are speaking from different directions, and you can see that the IPDs for the different speakers are indeed different, so the neural network can use this information on the input to better differentiate between the different speakers or different directions. The second option is learned spatial features, where instead of having this fixed computation of the IPDs, we simply input the signals, here they are in time domain, to the input of a convolutional layer, which can learn to extract some kind of spatial features. The parameters of the convolutional layer here are learned jointly with the full network, so it can learn some optimal representation or optimal information extracted from the multi-channel recording to help the neural network. These spatial features which are extracted would be again added to the input of the neural network. In a recent work of Katalin Zorilla, the authors compared the fixed IPDs with the learned spatial features, and what they showed, here these are again SDR scores, so higher the better. And so using any kind of spatial feature is significantly better than using no spatial feature. And in anechoic case, the learned spatial features have like very significant advantage compared to IPDs. But in a reverberant case, they are only slightly better, and I would actually say comparable to the fixed IPDs. And this is maybe, I would say, the more realistic scenario to have reverberation in the signals too. The next multi-channel approach is using fixed-based beamforming with stream selection. In this approach, the multi-channel signal is used as input to a set of fixed beamformers. These fixed beamformers are designed so that they focus into different directions in a grid. So, for example, here they would focus from direction 0 degrees all the way to the direction 330 degrees. The outputs from this set of fixed beamformers are then combined using weights derived from the enrollment information. So here this combination using the enrollment information should allow to select such streams that contain the speech of the target speaker. After these outputs are combined, we should get enhanced spectrum where hopefully the target speaker is enhanced, but this can still contain some interference from the other speakers or noise, and that's why here in this work there is also a single channel target speech extraction method applied on top of this processing. Finally, I will also talk about location-guided networks. Again, this fourth approach is different from the first three ones because it also assumes having some spatial information about the target speaker as part of enrollment. So we know the position of the target speaker, or at least approximately we have some information about the position of the target speaker. This additional information can be, for example, in the form of direction of arrival. Such information can be obtained, for example, from visual information when we have also camera recording the scene. Or we can have a multi-channel enrollment signal which was recorded from the same spatial position as the mixture. So from this multi-channel enrollment signal we can also get some information about the position of the speaker. There are two possible location-guided methods that I will describe here, either target location features or spatial preprocessing. In the case of target location features, we take the known direction from which the speaker is speaking, and we extract some kind of features that we can then use at the input of the neural network. Here is one example of such target location feature that is called directional power ratio. This feature is again based on fixed beamformers, where there is one fixed beamformer. This picture shows beam patterns of the fixed beamformers, and one fixed beamformer is designed to enhance the known target direction. And then there are other beamformers which are again designed to focus on different directions in a grid. The directional power ratio then measures the ratio of energy of the output of this beamformer in the target direction and sum of energy of outputs of all the fixed beamformers. So this ratio will be in the end a value from 0 to 1, which should be closer to 1 for the time frequency bins where the signal from the target direction is dominant. In that case, the output of this green fixed beamformer will be the highest, so this ratio will be closer to 1. So in the end, what we get from this is something similar to time frequency mask. Here you can see example of what this feature would look like, and you can also compare this to here the power spectrum of the clean target speech. So you can see that actually it is high in the areas where the target speaker is dominant. Another option, when we have some information about the position of the target speaker, is to use spatial preprocessing. In this case, we design a beamformer which should enhance the target direction, either again from the information about the direction of arrival, or also in the case when we have the multi-channel enrollment utterance, we can estimate the beamformer using this multi-channel enrollment utterance. This beamformer is then used to enhance both the mixture and the enrollment utterance, so both of them are somehow pre-enhanced, and then still the conventional target speech extraction processing is applied on top of that. In this case, in these papers, they also use mask-based beamforming on top of this. In these papers, this method was tested on a scenario of changing speaker positions. So in this paper, some knowledge about the position of target speaker was available, but still the position could change a bit. And this paper showed that even when the position changes a bit, this approach can still enhance the target speaker very well. And this is the conclusion of this section. We have seen that spatial information can improve the quality of the extraction. If we have also available some information about the position of the target speaker, we can use location-guided approaches, such as location features or spatial preprocessing. And when we do not have the knowledge of the target position, but we have a multi-channel recording, there are several approaches that can be used, such as mask-based beamforming, fixed beamformers, or spatial features. These different methods basically differ in the level of how much the neural network uses the spatial information. When we use spatial features, we directly input the spatial information on the input of the neural network, which has the disadvantage that the neural network can overfit on the particular microphone array or particular positions of the target speaker. On the other hand, in a simple mask-based beamforming, the neural network works only on a single channel only. So the neural network itself doesn't use any kind of spatial information, so it is independent of the microphone array, but can perform a bit worse because it is not making use of the spatial information. And then the fixed beamformers with subsequent selection is somewhere in between in this regard. So with this, I will finish this section. Again, in the slide, you can you find some references, and if you have questions, then please now you can ask the questions.
So there's actually one question on the QA, actually two. The first question is, could you elaborate more on the intuition of generalized cross-correlation? Can you comment on that?
Can we also keep the slides so that I can show a slide? So here the generalized cross-correlation basically measures a difference between sorry, I maybe need to think a bit about that. So the generalized cross-correlation is a method which is very often used to estimate the delays at different microphones. If speakers are speaking from different directions, that will result into different delays at different microphones. So here we can basically compute such delays for each time frequency point, and in the case when the signal is coming from a similar direction, these delays should be similar, at least inside one frequency bin, and different for speakers speaking from different directions. If you want to know more, actually maybe on this slide, Maybe I am missing the reference for this one, but this spatial feature was tested in a paper about multi-channel deep clustering. I am now not 100% sure whether it was also in this paper, but if you look for multi-channel deep clustering, there many different spatial features were tested, including the generalized cross-correlation. But anyway, the generalized cross-correlation performed quite worse than the other features, such as IPD.
Then there is another question that is, can TSC system compensate for DOA estimation errors? If DOA is estimated wrong, can the output of a TSC system be still acceptable?
So the approaches where the DOA was used were the location-guided approaches, where in the spatial preprocessing case, this was explicitly tested in the papers. So there were changing speaker positions. So the direction from which the speaker is speaking was not fixed. For the target location features, I am not sure. I don't think that this was explicitly tested. But since here the location features are processed by the neural network, I think it should be able to handle it in the case when you have such examples also in training data.
Okay. Maybe I think we will maybe move on with the rest of the presentation, but if you have questions again for this part of the presentation, you can still put QA here and Katka can answer by the chat during my presentation, or we can go back to that at the end. Yes, so maybe the follow-up we can discuss after Daniel has the follow-up questions, but I think I can present the next, right? Katka?
Yes, we can move on to the next part, I think.
Okay. So now I'm taking control. Okay. So the next part is about target speech extraction using visual or multimodal clues. So Katka introduced audio-based or enrollment-based approaches, and also she just spoke about locational feature-based target speech extraction. And I will now present an approach that uses the video or visual information to do the extraction, or eventually multimodal clues. So visual information is investigated a lot in a speech processing field. For example, there's lots of work on lip reading or audiovisual ASR, or using audiovisual voice activity detection, source localization, speech enhancement, and so forth. And of course, here we focus on the problem of extraction, where we extract from a speech mixture. And I want to emphasize that there are early works that show that visual information could be helpful for separation. But here, again, we focus on the most recent deep learning-based approaches. So this is a schematic diagram of a system that used visual clues for performing target speech extraction. And basically, you would have a video that will record the face of the target speaker speaking in the mixture. And we will use this video as a clue to inform the target speech extraction, which of the speaker to extract in the mixture. And the studies that use visual clues are backed up by studies in neuroscience that prove that the visual clues can help humans also to focus their auditory attention on particular sources. Also, one other interesting property of using visual information is that obviously it's not affected by the acoustic noise. And also, we've seen that when using audio clues, it has some trouble to discriminate speakers when the voice characteristics are similar, but the visual clues may not suffer from the same problem. So in this section, there are like 3 categories of approach that using different clues. So approach that you would use video clues. related approach that would use still image, so only a picture of the target speaker, and approach that would use multimodal clues, which means several clues, for example, video, enrollment, etc. And here, because of time constraint, I will skip the approach that use a still image, but we included some reference to this approach. So if you're interested, you can find pointers to those. So let's go into the video clue-based target speech extraction. So this right figure here shows an example of a typical video clue-based target speech extraction system, where again we have here the video clue and the mixture here. So this follows a similar architecture as the audio clue-based approach, although we use slightly different terminology in most of the works. So the video clue will be processed by a video encoder. So that could be the embedding extraction part of the audio parts or the auxiliary network. And the mixture will be processed with an audio encoder, which is simply the lower layer of this extraction neural network. Here we have a fusion layer which combined both the audio stream and the video stream, and this was called the adaptation layer in audio part. And then on top of that, we have some extraction module, which is simply the upper layers of an extraction network. And here I want to emphasize that since we are using a video of the target speaker speaking in the mixture, now the time series is aligned with the audio. That means that the information contained in the video is completely related to the speech of the target speaker. And typically, the duration of the video, T here, is the same as the mixture. So I will go into the details of each component of this system. And we will start with the video encoder, which is the most different part from the others we discussed so far. So the video encoder here will consist of two steps, the video preprocessing and the video embedding extraction. For video preprocessing, if we have a video of several speakers speaking in a room, for example, we first need to find the faces in the video, and we can use off-the-shelf face detector or tracker systems such as Viola drones. Then we need to select the face image of the target speaker, and this would be application dependent, but in most of the work we'll be presenting, we assume that the user selected one of the speakers. And then we need to crop the video to include only the face or the lip region of the target speaker. Next, we input this cropped video and input that to video encoder that outputs a sequence of video embedding vectors, ESV here. So it's important to see that the output of the video embedding now is a time series. It's not a vector like for audio, it's a time series. And the embedding vector should capture information that would be relevant to extract the target speaker. So that may be, for example, the mouth opening and closure regions, but that could be also finer lip movements that could identify, for example, the phones that is spoken by the target speaker, for example. And for the video embedding, we will see two large categories. So the first one is learned jointly with the extraction network from raw videos, and the other are embeddings that are derived from intermediate representation. So first, embeddings or video encoder that are learned from raw videos. It's similar to the audio extraction where we also learn the auxiliary network simultaneously with the extraction network. Basically, it consists of training the whole system from scratch by using mixture and raw videos and giving the target training samples, the target speech as references. So this kind of approach have shown some promising results, but basically for a speaker closed system, where it was trained and tested on the same speaker. And it may be difficult to extend to speaker open because it may require a large amount of data to learn general and meaningful video embeddings directly from raw videos. So actually, most speaker open approaches that have been developed afterwards are using intermediate representation. So approaches that use intermediate representation can exploit a pre-trained system to generate meaningful embeddings. So the advantage of that is that we can leverage a large amount of data from video or image tasks, and therefore we can obtain a more robust representation, a more robust embedding that can be robust, for example, to phase variation, resolution of the image, luminosity, etc. Of course, if we use a pre-trained encoder, this will not be optimized for the task of speech extraction. So on top of the pre-trained encoder, usually we would add a few transformation layers to make the representation, or the embedding, optimal for speech extraction. And here again, we can see two subcategories in this category here. There are embeddings that are obtained from phase landmarks and embeddings that are neural embeddings that are pre-trained on different tasks. So first, the phase landmarks approach. So here, phase landmarks represent position of key points in a phase. So as shown here, it can represent, for example, the mouth, the nose, eyes, etc. And some studies show that we can use the XY coordinate of the phase landmark or their derivative as video embeddings. So these phase landmarks are very fast to compute, and also they are very interpretable. And it has been shown that they can be used for speaker open target speech extraction, even with a small corpus, such as grid corpus. However, these approaches were mostly used with relatively small data sets, so it remains to be tested for larger tasks. The other approach are neural embedding pre-trained on different tasks. And one example of this is neural embeddings that are pre-trained for face recognition. And typically, most studies would use the FaceNet architecture that is widely used for face recognition. And we can see here an example of this architecture. And this, of course, is trained or pre-trained to recognize faces. So the representation is not directly related to the acoustic content. However, there are studies that show that intermediate representation of FaceNet contains information about the face expression. So to perform targeted speech extraction, usually an intermediate layer is used so that it can keep face information such as the mouth position, etc. So the advantage of using such kind of pre-trained embeddings is that because they are trained on static image with ID of the speaker, although they cannot model the lip movement dynamics, so that's maybe a drawback, but the advantage is that there are lots of training data, and it's quite easy to get training data, so it's easy to train very strong embeddings. The other approach is to use lip reading to pre-train the video embedding extraction part. So this is as in this figure here, where we'll have a video as an input, and the network will predict word or phone. And again, you can use intermediate representation as embeddings. So this representation will be directly related to acoustic content, because obviously we try to predict phone or words. It's trained on video, so it can learn to model the lip movement dynamics. However, to train such a network, we need to have video and the associated transcriptions for training. So you can think that it's much more costly to get a large amount of training data. And finally, the final approach is to use synchronization as a subtask. So this synchronization consists of having a network that inputs in one branch the video, and in another branch waveform or audio of the video and try to predict whether both are aligned or not. And there are studies that showed that an intermediate representation obtained from this pre-trained network can be used for target speech extraction. And here, the embeddings will be related to the acoustic content. There is here this audio part of in the network. It is trained on a video, so we can learn probably the lip movement dynamics. And also, it's a self-supervised training, so there is no need for transcription, which may be an advantage because we can therefore get a large amount of training data at a very low cost. So I've described here the video encoder part. I would like now to explain briefly the other parts of the network. And first, the fusion layer. So the first thing we need to realize is that the audio, typically the audio and the video use a different sampling frequency. And therefore, the works usually either upsample the video to match the sampling rate of the audio or downsample the audio. And then for the fusion, after doing that, the fusion itself is very similar to what has been done for audio. It can be concatenation, multiplication, or even factorized layer. For the other parts of the network, the video encoder, typically it will use convolutional layers as it is widely used for image processing. And for the other components, so depending on the studies, there are some proposal of particular architectures specific for the audiovisual extraction, but actually some studies also use architecture similar to the one used for audio clue-based approaches. And for example, Timedomain conv-TASNet models are recently shown to perform quite well on this task too. Now I want to say one word about the training data. So again, to generate training data, we need to have the mixture here. We need to have the reference target speech signal. And also we need to have a visual clue of the target speaker. So what we would do is we would use a data set that includes videos of single speaker speaking. And we would take 2 videos and take the audios of each of these videos to create the mixture and take the video of one of the speaker as visual clue. And the mixture will sound something like that.
And the question for us now is, how much can we...
So when we want to extract the speaker A, we don't use speaker B video. So now I would like to show you a concrete example of one of the successful system. Again, there are many systems that have been developed. So this is just one example of one of the early quite impactful work, I would say. So this is the looking to listen work. So here it's a description of the detailed architecture of the network. But to summarize, it used for video embedding, it used FaceNet, so pre-trained on image recognition. The fusion is using concatenation, and the extraction is done in the frequency domain. In terms of performance, we see here the SDR of mixture of male, male, female, female, and male, female. And we see, we can notice that actually it achieves good performance and stable performance even for same gender mixtures, which is one of the nice property of a visual-based extraction method. I would like to play you one example, which is taken from this web page. So you can, if you're interested to listen to more samples, there are many examples there. So I will play first the mixture.
Hate being on planes. In general, there's so many noises. You know what I mean? I won't flush the toilet on an airplane because of the noise. Like, it scares me.
And then the extracted left speaker.
Because he might say, my stripes are solid. And I'd say, uh-oh, I'm talking.
So I think you can perceive that it extracts quite well the target speaker and also suppress the interference speaker also very well. So So to summarize, for the video clues-based approach, we can see that it performs competitively with audio-based approach, and I think that's quite remarkable that using the video clues, we can still perform target speech extraction quite well. And also, it is particularly advantageous when speakers have similar voice characteristics. There is one example in the paper, which is an extreme case where they actually mixed the speech of the same speaker, of course, speaking different utterance, but still, by providing the video information, they can extract the voice of the speaker, even if it's the same speaker. So there are some issues when using the video. So I mentioned that the sampling frequency was different between the audio and video, but in general, if you use a codec or something, sometimes there may be some synchronization issue between the audio and video, and some work proposed to include a synchronization module within the extraction network to accommodate for that. Also, some people raised the issue that there may be some privacy concern when using the video, and that user may be more willing to provide still image, so picture of the target speaker instead of a video. And there are at least 2 works that they use still image to do extraction that show that it was possible to perform some extraction, but I would say that the performance still are far worse than the performance that would be obtained with video or with audio. But this is quite interesting. I think that it's still possible to do some extraction with still images. And another issue is that when you have a video clues, sometimes the face may be occluded. So if your mouth is covered by your hand or you're looking in another direction, the visual clue may be corrupted. So it's important to make the methods that are robust to this kind of situation. And this is where multimodal clues can be handy. So we'll now explain a multimodal clue-based target speech extraction. So as I've just mentioned, when you use a visual clue-based approach, you may have occlusion, and then the visual clue may not be very reliable. For audio clues, you may have noise in the enrollment, or the mixture may have similar voice characteristics. And if you use DOA, you may have DOA errors, or the 2 speakers may speak from a very similar, close to each other, and therefore the DOA may not be very helpful to identify the target speaker. So you can see that depending on the clue and the situation, sometimes the clue may not be very reliable to perform target speech extraction. So several people have proposed to use multimodal clues, so several clues, to perform target speech extraction to be more robust to this kind of corruption of the clues. For example, many propose to use video and audio, but also there are work that use face and audio, or video, audio, and location. Here, I will just introduce the video and audio-based approaches. So when you use audio-visual clue-based approach, you would typically combine video encoding and video embeddings and audio embeddings, as here. And typically, all the components of the system are similar to what we have discussed so far. But then we need to have a clue fusion that will fuse both the visual and the audio clues. There are 2 main approaches to do the clue fusion. The first one is simply concatenate the video and audio embeddings and then pass them to the fusion layer. And the other approach is to perform to select the embedding based on the clue reliability with a weighted sum. So this idea is that, let's say that the video is corrupted because of some occlusion, then we should put more weight on the audio enrollment, on the audio embedding, than on the video embeddings, and a small weight on the video embeddings. On the opposite, if, for example, the audio clue is not very reliable because, for example, the 2 speakers have similar voice characteristics, then we should put more weight on the video embedding than the audio embedding and use dominantly the video embedding part. So this is what is proposed to be doing by doing a weighted sum where this weight can represent the clue reliability. And to compute these weights, we can use an attention mechanism that inputs a representation of the mixture and also the audio and the visual embeddings and compute these attention weights. You can notice that the concatenation is actually similar to attention fusion with a fixed weights set at 0.5. And also, to ensure that the attention weights really model the reliability, we can actually guide the attention weight during training to help a better clue selection. I would like you to see some results of this multimodal approach, which here we present results with a multimodal speaker beam. So here the data is created by a mixture of 2 speakers where the data is taken from the lip reading sentence 3 corpus. And we investigate clue corruption with audio clues and visual clues, where for the audio clues, we added white noise at SNR of -20 dB, 0, and clean to the enrollment. And the video clues, we added a mask to mask the mouth region or completely mask the video. Here, the results are shown in terms of SDR improvement for the audio only, video only, and for multimodal approach with audiovisual concatenation and audiovisual with the attention fusion. First, you can see that when we use only one modality, one clue, we can get quite a good performance when both when the clues are reliable, but the performance would degrade quite severely when the clues are not reliable anymore. However, if we use multimodal clues, we have a stable performance and robust performance in all cases. And also we observe a slightly better performance using the attention-based fusion compared to the concatenation in our case. And I would like to say that if you want to listen to some sound samples, there is some demos on this web page here. So please have a look. And now I will conclude the audiovisual and part of this tutorial. So first, we need to, I want to emphasize that it's possible to do extraction with video clues, and it works quite well. But what information is actually really needed is still, I think, an open question. So definitely, maybe fine lip movements are needed, or maybe actually speaker activity is mostly sufficient. I think if we can better answer this question, it may be useful to design very practical and maybe lightweight systems, for example. We've seen that to develop robust system, combining speaker clues is probably a good strategy. We've seen some examples with audiovisual, but also I mentioned that more clues can be also used. And for example, there is a system here that uses audio, visual, and locational clues, all of these clues to perform target speech extraction. There are some issues when using a multimodal approach. And for example, one of the issues is that one of the clues may be dominant during training. So, for example, if the audio, if it's easier to solve the task using only the audio clues during training, maybe the system may not be trained to use the video correctly. So it needs to be carefully, the training needs to be carefully designed so that both clues are really, the model learns to use both clues. And finally, I would like to recommend you this overview paper if you're interested in the topic, because it covers quite in details the audiovisual speech enhancement and separation approaches. Okay, so I think we have a little bit of time for questions.
Just a comment that the streaming was interrupted, but for us in Brno, the stream worked well, so I'm not sure if many people experienced this. But maybe if anyone wants, like some particular slide to be quickly summarized again or something like that, you can ask for it in the chat. So if there are no more questions, should we just continue with the next section?
Yeah, I think we can. And if you have question again, you can add it to the QA and I can answer after. So yeah, we can go on. I think.
So I will start this question and then after like 5 minutes, Marc will continue.
So you can, I think you can start.
Okay. So in this section 5, we will talk about some other tasks that can also benefit from having the information about the target speaker. In particular, it will be diarization presented by me and then speech recognition presented by Marc. So I will start with some short talk about the diarization. So in diarization task, on the input we have a long recording where many different speakers are speaking. And the task is to detect who spoke when. So basically to get the speaker activity of all the speakers. In theory, if we have enrollment utterances for all the speakers, it could be even tackled by target speech extraction in combination with voice activity detection. So we could first apply target speech extraction to extract the signal of a particular speaker, and then on the extracted signal applies voice activity detection to get the speaker activity. And we could do this for all the speakers that we are interested in. This is, however, not so often used in practice, and it is mainly because this is basically attempting to solve more difficult tasks than necessary. In the end, we want to get only the speaker activity, and here we are trying to extract exactly the signal of the target speaker, which is more difficult. So instead, what we can do is to directly use a block which takes the recording and enrollment utterance on the input and outputs the activity of the target speaker. First work that did something similar to this is personal VAD. In a normal VAD, voice activity detection, we try to differentiate between two classes, speech and silence. In a personal VAD, we instead differentiate between 3 classes: target speech, non-target speech, and silence. The personal VAD in this work was based on a neural network, which was informed by the vector of the target speaker. You can see a small summary of the achieved results here. These are classification accuracies, and you can see that the personal VAD can achieve quite high accuracy while having much less parameters than if we did VAD with subsequent speaker verification on top of that, because here the speaker verification system has quite a lot of parameters. So using the personal VAD can lead to quite a lightweight system that has also good classification accuracy. The personal VAD, at least in this work, was applied only to recordings that don't have overlap. So at all the points, at maximum 1 speaker was speaking there. A work called Target Speaker VAD somehow built upon this and was applied also on data with a lot of overlaps. Target Speaker VAD was developed for Chime 6 challenge, which contains very highly distorted and also very highly overlapped data, and it was very, very successful in this challenge. It had the best diarization, I would say, by far compared to the other participants. In the target speaker VAD, we have a single speaker part of the model, which is informed by I vector of the target speaker and outputs activity of this speaker. And then in this particular data, there is fixed number of speakers. There are always 4 speakers. So in TSVAD, they also employed a model which combines the activity of the 4 speakers to get improved estimation of the activity, basically the diarization. Recently, there has been also extension, which can be applied also to unknown speakers. Here there is some summary of the results of TSVAD. These are diarization error rates, the smaller the better, and it is compared to more conventional clustering approaches to diarization and also end-to-end diarization approaches, which are recently quite popular for diarization. And on this particular dataset, CHIME6, the TSVAD is indeed much, much better. Since we covered also visual clues in this tutorial, I will also mention that there are diarization or voice activity detection approaches that also make use of the visual clue. One particular example is a method called TalkNet that on the input has a cropped face video of the target speaker and the input recording, and the output should be binary classification of each frame saying whether the target speaker is active or not. The model basically consists from a visual encoder, audio encoder, and some part that combines these both streams using cross attention. This is one example of such work, but there are many more works that use the visual clue for detecting the speaker activity. You can find a nice list of references at this link, which was compiled by the authors of TalkNet. And now I will pass the word to Marc, who will continue with speech recognition.
Okay. Thank you, Katka. So, yeah, there have been a few questions about the video-based approach. I would like to take these questions maybe at the end of the presentation. So I will go back to that after. So I would like now to introduce to you how target speaker clues can be used also for several problems of ASR. One of these problems is the target speaker ASR, where we have an ASR system that inputs a mixture and an enrollment, and output the transcription of the target speaker speech only. A related problem is what is called anchored ASR, where instead of the enrollment, wake-up word is used to inform the system which is the target speaker. And finally, we'll see also that meeting ASR, so that aim at transcribing the speech of each of the participants in a meeting, it can be also useful to use speaker clues in this context. So I won't go into the details of the ASR architecture, but I just want to mention that there are basically two main types of ASR systems that are still in use, like hybrid, so DNN HMM hybrid systems and end-to-end system. Basically, what I want to say is that most of the works we present here can be used either hybrid or end-to-end system, but they can be applied to both of them in general, or have been applied to both of them. So I will first explain the target speaker ASR. So target speaker ASR can be realized with two schemes. The first scheme is to do target speaker ASR with explicit signal extraction. And this is simply a cascade connection of a target speaker extraction, target speech extraction module and a ASR module, like shown here. And here we will discuss approach that use enrollment-based approach, but similar thing can be done also with other clues like video clues. So there have been quite some work that perform such a target speaker ASR. And for example, some approach using a single channel or multi-channel target speech extraction as a front end. And if you use multi-channel, you can after perform beamforming, and then there is usually a feature extraction to compute feature that are suitable for ASR. And at the end, you have ASR backend that is ASR that recognize speech of a single speaker. So it assumes a single speaker input here. So all the extraction is done in the front end. The advantage of this approach is that we have intermediate access to the extracted speech signal, which can be useful in some application and also nice when we want to develop the system and debug the system. There is a related approach that instead of working to do the target speech extraction on the signal itself, it does the target speech extraction on the feature domain. So after first it performs the feature extraction and get feature suitable for ASR, and then does target speech extraction on these features. And this has been shown to be advantageous in terms of providing capability for online processing and low latency. Of course, one issue when combining target speech extraction, or at least in general a speech enhancement frontend and ASR backend, is to have a good interconnection between both components, so that to reduce the effect of distortion of the speech extraction frontend on the ASR. And you can use several approaches to do that. For example, some people have proposed to modify the training loss to avoid oversuppression, or also processing only, for example, overlap speech regions of the signals. Also, simply you can retrain the ASR system on the speech processed with the TAC frontend, or actually more sophisticated work actually perform joint optimization of the ASR and the target speech extraction frontend. Basically, the ASR consists of a neural network. The target speech extraction is also a neural network. And in between, you may have the beamformer and the feature extraction that are fixed modules, but it's possible to differentiate. So it's possible to backprop through the whole system and optimize the target speech extraction frontend for the ASR criterion. The other way to realize target speech ASR is without explicit extraction. So in this case, it consists of a single modules that directly transcribe speech of the target without explicitly extracting the speech signal. So this is actually related to relatively older work for acoustic model, speaker adaptation of acoustic model. And one common approach to do speaker adaptation is to add to the input of a acoustic model or ASR model, to add a speaker embedding, typically I vector, that will represent the voice characteristic of the target speaker or of the speaker. And this enables to adapt the ASR model to the voice of the input speaker. And these studies usually assume that there is only a single speaker at the input. And in this case, the speaker embedding can be computed directly from the input speech. And basically, you can think that you can apply similar ID to realize target speaker ASR. And instead of having a single speaker as the input, you would have a mixture. And instead of computing the embedding from the input speech, you would compute it from the enrollment. But in principle, it's very similar architecture. And now the idea is that by providing this embedding to the acoustic model or to the ASR system, you would guide the ASR system to recognize only the speech of the target speaker and ignore the interference. And this can be actually realized by adding adaptation layer, similar adaptation layer that Katka introduced within an ASR system. And this has been done for hybrid system and also for end-to-end systems. And this adaptation layer can be put at different parts of the ASR system. So here I would show a result comparing both target speaker ASR without explicit extraction on the left here and with explicit extraction on the right here. So in this study, we evaluate end-to-end ASR, and the task is a Wall Street Journal 2 mixed. And for all systems, they were jointly trained from scratch. So the system that don't use any explicit extraction, we simply add an adaptation layer to the encoder of encoder-decoder end-to-end ASR system. And for the system with explicit extraction, it's a cascade of single-channel speaker beam where we compute a mask, and then we extract the target speaker. We have the feature transformation, and then we have the end-to-end ASR, which is a similar end-to-end system to the left one here, except that we don't have the adaptation layer. So it's a very standard encoder-decoder ASR system. You can see the result on the right here. So this indicates the word error rate, lower the better. So in blue, you have the result without any target speaker ASR. And you can see that the results are very bad because the system cannot identify which is the target in the mixture. And in green and red, you have the result without explicit extraction and with explicit extraction. So you can see that both systems actually greatly reduce the word error rate and achieve quite nice performance. And we can observe actually a little bit better performance with the explicit scheme, but I would say that it's a bit difficult to compare, and I would say that this may not be so significant because the scheme without explicit extraction is much more compact. There is only end-to-end ASR with only adding this adaptation layer compared to this scheme, which is a cascade of two relatively larger systems. And still, both systems performs quite comparatively. So I think that's quite remarkable that also, even without explicit extraction, we can achieve quite nice performance. And then the ASR system can really learn to exploit the embedding to just recognize the target speaker speech. So anchored ASR is very similar to what I've just explained now, except that it uses a wake-up word detector to split the input mixture into a wake-up component and the query speech, and it will compute the speaker embedding from this wake-up word. And then it can use a target speaker ASR or some similar kind of approach to perform the recognition. There is also a similar approach that has been done for multi-channel, where instead of computing speaker embedding from the wake-up word, it computes beamformer filters and use these beamformer filters to perform beamforming before ASR. Finally, I want to mention about the meeting recognition part. So again, meeting recognition means that we want to recognize and identify speech of all participants in a conversation. And we'll see that the speaker clue can help to solve this problem. And we will see that there are basically different schemes that can be taken. So one option is to use clues from enrollment or derived directly from the mixture. And another option is to use a parallel or a joint processing schemes. So I will briefly introduce these. So the first, how can we get the enrollment in a meeting? One way is simply collect enrollment for all the participants, and we can then get the embeddings for each of the participants and add this to a meeting ASR system. So the nice part about this kind of work here is that because we have embeddings for each of the speaker, we can link the transcription with the absolute speaker identity. So if we know that this speaker, let's say the name is Alice, and we have her embedding, we can say that Alice spoke blah, 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 blah. The other approach use embeddings or clues derived from the mixture. And typically, what we would do is we would apply diarization to first get some activity of the speakers. And one way to do after is to get speaker embedding from the single speaker regions of the meeting. And then we can use the embedding of each of the speakers to perform meeting ASR. There are other studies that instead of computing the speaker embeddings, they would directly use the speaker activity as clue for speech extraction. And here, obviously, the advantage of this approach is that you don't need to register the participants. You can directly get the clues from the mixture, so that's very practical. The drawback is that you cannot link the output, the transcription, with the absolute identity. You can just say that the first speaker said that, or the second speaker said that, but you cannot say Alice said that or something, because you don't know the mapping between, you don't know the actual identity of the speakers. So for meeting ASR, there are also two ways to do the processing. There's parallel processing scheme, which means that we decode for each speaker independently. So for example, one way to realize the meeting ASR is to perform target speaker ASR for each of the speaker in parallel, but that can be actually complex. And there are also schemes that do a joint processing so that they simultaneously process for all the speakers, which can be more efficient. There is one example of that, which is speaker attributed ASR, which I don't think I have time to go into the detail of this approach, but I just want to mention it, and I will present actually a result about this approach to show you that the speaker clue can be beneficial for actual meeting recognition. So I will show you here results of evaluation on real meetings that are taken from the AMI meeting recognition task, which consists of recognition of meeting from 3 to 5 participants recorded with a single distant microphone. And in this study here, mentioned here, they compared 3 schemes. One scheme is just to apply a diarization and then ASR. So by doing that, we actually cannot deal with the overlap speech in the ASR part. So the overlap region will affect directly the ASR recognition, the ASR performance. The other scheme is to do diarization plus separation. So after that, so there is here a separation inside the module to handle the overlap regions. And the last part is diarization plus the speaker attributed ASR, which means that it uses actually speaker embeddings estimated from diarization to perform meeting ASR. So this is the only approach that use the speaker clues within the ASR system. And we can see here the word error rate for the 3 approaches. And we can see that the approach, which is speaker attributed ASR, performs significantly better, which shows that the speaker clues can be actually quite beneficial for also meeting recognition too. So to conclude, I would like to mention that use of the target speaker clue can benefit ASR or diarization. And for example, the target speaker VAD was achieving state-of-the-art performance for the Chime 3 task. And also the speaker clues can be beneficial for some ASR tasks too. There are also works that show that target speech extraction can also be beneficial for other tasks such as speaker verification. And there are actually various configurations, and I want to say a few words about that. First thing is I want to mention that most of the work that I've described here are actually backed up by studies that, similar studies that do similar stuff with separation. So for example, there is a multi-speaker end-to-end ASR that includes a separation capability within an end-to-end ASR system, which is shown here. So in the encoder, you would have a layer that would split between the first speaker and the second speaker. And then you would have recognition. The attention would output the sequence for the word sequence for the first speaker and for the second speaker. So the advantage of such approach is that we can recognize all speakers in the mixture, but we can argue that it may be difficult to identify which is the target speaker from the text output only. And compared to that, the target speaker ASR, there is no speaker ambiguity at the output, which may be a clear advantage. We've discussed that there is, it's possible to do target speaker ASR with or without explicit extraction. So I presented results of both methods, but it's actually difficult to conclude what approach is better in terms of performance because of the different configurations. Maybe we can still have some comparison of advantage or characteristic of the systems. Potentially, the system with explicit extraction may lead to a larger model, But they may be easier to deploy with existing ASR system because we can just focus on developing the front end and use already developed ASR system, single speaker ASR system. And also because we output the speech signal, we can have probably better interpretability. In contrast, without explicit extraction, we may have a more compact model, but it's a black box, which may be more difficult to deploy because we need to design a system from scratch. And it's also less interpretable because it's a black box. And finally, as I mentioned, here I describe approach that use the audio clue to perform target speaker ASR, but you can also use visual or visual and locational clues, as shown in these works. And I don't know if there are many questions here, but I think I could probably go on with the conclusion, and then we can have a more overall discussion. And if you have questions, yeah, I can answer at the end. So let me now conclude this tutorial and present some future work, future direction. So first, we introduced a target speech processing, and we show that there are various ways to realize it using different clues like audio, video, locational clues, and different configuration of the neural network. Also, we show that these technologies can be used for various tasks such as enhancement, voice activity detection, ASR, etc. So the problem is related to speech separation, but it can mitigate some of the practical issues with speech separation, which is the dependency on the number of sources and the permutation ambiguity. So it can be a practical alternative for many scenarios if we can have access to speaker clues. Also, because it is related to speech separation and because there are lots of progress, every week there is a new approach for speech separation. So you can actually borrow a good result for speech separation in terms of, for example, architecture, laws, or you can name it. And you can borrow these ideas and apply it to the target speech extraction. So this offers quite some opportunities for research. I would say that it's a field of research that is receiving increasing attention. So we show that some of the work for deep learning-based target speech extraction started in the 2017, and now you have quite some papers in this conference. Here is a list of obvious related papers. There may be more, actually. I want to mention some extension of the work we presented. One extension is integration of separation and target speech extraction. So speech separation can benefit from the speaker embeddings. We've seen that the embedding can improve the separation performance in the introduction. And also the speaker embedding could enable the tracking of the speaker for long recordings. And there are some works in this direction where the speaker representation or the speaker embeddings are learned from enrollment of all the speakers, or they are learned from mixture. And one example of such an approach is the wave split, which is shown here, which actually have a first stage which do embedding extraction directly from the mixture. So it gets two embeddings. If it's a mixture of two speakers, you get two embeddings, one for each speakers. And you input these embeddings to a second step, which is a separation step, which is a conventional separation approach, but that also use this embedding as auxiliary input, and then it performs separation. And actually, this wave split was shown to perform quite well on speech separation. Another extension of the work is to apply this method to other signal than speech, so target sound extraction. For example, we can have a mixture. If we walk in the street, we can have a mixture of several speakers, but also dogs, sirens, cars, etc. And maybe we want to just take attention to the siren. So we can develop systems that extract only some type of sounds and not the others. So I will have a presentation about this kind of work. So on Thursday. So if you're interested, please come and join my poster. Also, I think there is quite some interesting work done on guiding the speech extraction using brain signals such as EEG. So this is a very challenging problem. It's attracting quite some interest because if we can do that, it can have very practical application, of course, for hearing aids, because the people could guide the hearing aid to emphasize the speech of the speaker he wants to listen simply by decoding the attention mechanism of the speaker brain of the listener. Finally, I will conclude with some future directions. So one important direction is to investigate more diverse acoustic conditions. For example, dynamic condition, various recordings, more realistic. And if we do that, there may be a mismatch between the training and testing conditions. So one thing that we believe it's important is to develop techniques that can adapt the system to the deployment condition. And when we mean adapt to deployment condition, we may not always have parallel data to do the adaptation of the system. For example, we have just a recording of a mixture without the actual target speech. So we need to think about ways to adapt the system in this kind of situation. And one work in that direction will be presented by Katka in an oral presentation on Wednesday. So please join that presentation if you're interested. Then one thing I also believe it's quite important is to have more investigation on the target speaker representation. And this will go to have better discrimination and more robust representation. So this may be actually a trade-off between both. So for better discrimination, one obvious case is when we use audio clues to improve the performance for same gender mixtures. And also one point that was actually addressed in the question at the beginning is what I would say the false positive. What would be the behavior of the system if we have a mixture of two speakers, but we use a clue of a different speaker that is not active in the mixture? So we want the system to output a zero signal in this case, but this scenario is actually not sufficiently investigated, I think. I think there is one study in this conference that will deal about this problem. But this is, of course, very important and practical issue that should be more evaluated, I think. In terms of more robust representation, we want to have a speaker representation that is robust to the different recording conditions, noise, room, speaker, health condition, for example. So I'm not saying that the current representation are not robust enough. I'm just saying that they are not well investigated, and it's not always easy to investigate these conditions. But typically, even if the target speaker has a cold, we still want to be able to extract his voice. And finally, as I mentioned, one important application of the technologies is to have hearing aids or hearables. But if we want to use these technologies for hearing aid and hearables, we need to have online processing or lightweight processing. So there are some work in that direction, but still it's still a very important line of direction. And most of the approach we described are, I would say, quite computational intensive and are not really aiming for online processing yet. Also, you can probably think about other clues that could be useful to solve the problem. So that will conclude the tutorial. Thank you very much, and we're happy to answer questions. I think we still have 10 minutes at least for answering the questions. And again, the slides and some materials is available on this webpage. And also Katka briefly described the code that we released actually for this tutorial, which is implementation of speaker beam based on asteroid. So it was a bit difficult here to make demo or like show the code in details by sharing the screen or something. But yeah, I think you can have a look at it, and if you're interested, you can use that. Okay, so that will close the tutorial, and I want to answer a few questions that remain in the QA. So there was one question about the visual embedding that is trained with words or phones is self-supervised, and can you please explain how this is done without word labels? And I want to mention that actually I presented 3 ways to pre-train the visual embeddings, and one was from the face recognition, one was from a word or phone recognition, and one was using synchronization of between the audio and the video. So the third approach for the synchronization can be using a self-supervised. So you can basically create data by mixing, modifying the audio and the video, and then you can create data to train the network. So it's not the method that use the word prediction that is self-supervised. I don't know if I answered the question.
There is another question that maybe I can address about whether the audio TSC models are language dependent, and whether a model trained on English can also be applied on speech in other languages. So I don't know about any work that would rigorously test this, but I think we have some practical experience with this. So at some point we developed a speaker beam demo, which we were showing at a conference. And with this demo, we often tried to speak. It was trained on English, I think, and we often tried to speak like Japanese or Czech or just any native language of a person who came to the demo. And basically, we have seen that it works quite well also on the different languages. Maybe if we did some more rigorous testing, then we would possibly see some drop in the performance, but at least we have seen that it doesn't completely break when you speak a different language at it.
So maybe I can address the other question from Shinji Watanabe that asks, can the text information be a clue? For example, if we know the transcription of the target speaker, can we extract the target speech? So I'm not aware. I mean, I would say that there is a work I'm aware of that use for the keyword-based multi-channel approach. Basically, they use a network that predicts a time frequency mask, and this network is trained to predict a time frequency marks for the keyword. So it can discriminate the keyword from the other speaker somehow. So in a way, it's possible to, it shows that it could be possible to extract based on the text. I'm not sure there's any studies that does text-informed, text clue-based extraction. There are some works, of course, and I think you're aware of that, for speech enhancement, when the noise, speech plus noise, to use the text as a clue to improve the noise reduction. There are some works in that direction, but for speech mixture, I'm not sure. And actually, I think that's one of the potential interesting clues to investigate. I hope I answered this question. Maybe, Katka, you could say, I don't know if everybody is following the QA, but maybe you can mention about you answer for the real-time processing.
Okay. So someone asked about whether the models can be applied for real-time processing, and in general, I would say that this is also not very well addressed in the literature so far. Many of the models that are used today are not causal. They also use the future information, and there are also quite big models that require some computation to do the inference. So about the causality, this could be, I think, adjusted quite easily. For example, the conv.net, you can just make the convolution into a causal convolution, and this affects the performance a little bit, but I wouldn't say that it affects it a lot. But then still the problem of the model being very big and requiring some computation, this is still there, especially if you have limited hardware, such as hearing aids, then I think that these models are still too heavy. So this is still something that could be researched further.
So maybe I could also add one comment is that, so for ASR, there is voice filter light, which is quite, it's light, so it's targeting online processing and something like that. And also for the looking to listen paper, apparently they also recently developed quite efficient implementation, and it can be also applied for, actually I think it can already be tested for processing videos. So they showed that they could reduce the computational cost. I don't know how much the performance is affected by that, but yes. Mm-hmm. So there are some works in that direction, but
okay, maybe I can just continue on that note. There are also some works in speech enhancement that target this real-time application. And I would say that the developments in this could be also directly used in target speech extraction. For example, recently there was a deep noise suppression challenge that also was limited only to methods with very small latency. And I think that even at this conference there is a session about this challenge. So maybe if you care about the real-time processing and latency, you can also look at these publications. Do we have Marc back? No. So I don't see any other questions here in the QA.
There is one online question. Edson is asking to join.
Like a raising hand.
Yes, I tried to accept him. I'm not sure if I... Did it work out?
The person didn't accept it, so maybe it was just accident.
Oh, it was an accident. Oh, too bad.
So then maybe I would say that we are pretty much out of time. So also, if you have any additional questions after the tutorial, then you can still contact us, either through the virtual platform, if it's possible, or just at our emails, or if you meet me here at the conference, you can also ask me some additional questions.
Yeah, thank you very much for your attention and for your feedback in the chat. It was very nice to have the discussion with you.
Yes. Okay, thank you for your attention.